Whenever I mention that turboprops lose efficiency at speeds higher than around Mach 0.6, two propeller aircraft that fly faster than that inevitably get mentioned, as if that somehow invalidates the point. Those are the XF-84H Thunderscreech and the Tupolev Tu-95. I'm not going to deal with the XF-84H in this video since it never got past the prototype stage for very good reasons. The Tu-95 on the other hand was introduced in the 1950s, more than 500 were built until the 1990s, and it's still in service today. Its original purpose was extreme long range, made possible by the superior efficiency of turboprops compared with turbojet engines. But the Tu-95 was much faster than turboprop aircraft of the time, and even today it beats almost all modern turboprops in speed. The reason I say almost will become clear as the video progresses, because there's one big misunderstanding about how fast the Tu-95 really is that I need to address. The Tu-95 also had a few derivatives, including the Tu-114 airliner, and they all shared that remarkable speed. These are therefore turboprop aircraft that can fly well past the propeller efficiency drop-off point mentioned. To make this discussion mean anything, I need to set out a few parameters and define exactly what I'm talking about. Otherwise, I may get some angry comments. Many of you may already understand these concepts, but a quick revisit is in order since it's critical to what follows. We know that propellers can't spin indefinitely fast. Max RPM depends primarily on blade length, among other factors. For a given propeller RPM, the longer the blades, the higher the speed of the blade tips. Since the blade tips are the fastest moving part of any propeller, they are the most at risk of going supersonic, which is less than desirable. Okay, but why does propeller efficiency drop above a certain aircraft speed? Because the aircraft's forward speed adds to the speed the blade tips move through the air. This is called helical speed because the propeller blades move through the air in a helical path. Blade tip vortices show that path very nicely. So the effective speed of a blade tip is its rotational speed plus its forward speed through the air. For example, aircraft A is flying at 250 knots with its propellers turning at 2000 RPM. Aircraft B is flying at 350 knots with the same propeller RPM. If both propellers have a diameter of 2.5 meters, the blade tips on aircraft B are moving through the air faster than those on aircraft A, as the math clearly shows. This matters because there's a point at which blade tip speed starts to run into compressibility problems, and that point is often quoted as being somewhere around Mach 0.8. So why Mach 0.8 and not 1.0, the actual speed of sound? Because a propeller blade works much like an aircraft wing that produces lift. When the engine produces power, air moving over the suction side of the blade moves faster than the air on the pressure side, and more importantly, faster than the blade's overall speed through the air. That means the local airflow over the tip can reach Mach 1.0 even when the blade tip itself is only moving at about Mach 0.8. Mach 1 is not a hard limit on propellers. They can physically spin faster, but with a huge loss of propulsive efficiency. Once the blade tip gets to about Mach 0.7 or 0.8, compressibility problems begin. As the local airflow on parts of the suction side reaches Mach 1.0, a shock wave forms, causing a pressure rise, sharp deceleration, and airflow separation. What this means is that blade drag increases considerably, thrust decreases, and propulsive efficiency drops. Less engine power is converted into thrust, and fuel efficiency suffers accordingly. The shock I mentioned is also audible, and noise increases drastically when the tips have supersonic or transonic local airflow. So in essence, it's not a hard limit, but a soft limit that should be avoided. Just a quick aside on fuel efficiency. It is of course absolutely important to civil airliners, since profit margins are always tight and efficiency needs to be maximized. This is one of the reasons airliners usually want the latest and most efficient engines on their airliners. In the military, fuel efficiency is not necessarily as important because there are no profit margins after all. However, lower fuel economy affects range and endurance, and those are two things the military cares very much about. Keep this efficiency discussion in mind because I'll refer back to it later. Let's now go over how the Tu-95 is so fast. I'm sure it's no surprise that the contra-rotating props are a large part of why the Tu-95 is so fast, but it's not always understood why that is. In an ideal world, a propeller would move air only axially, meaning along the propeller shaft, with all of the imparted momentum contributing to thrust. But in reality, propellers don't work like that. They impart both axial velocity and tangential velocity, with the latter known as swirl. The airflow behind a propeller therefore has a helical twist. That swirl is kinetic energy that is not aligned with the thrust direction. Only the axial component contributes to thrust, the tangential component does not. So some of the work the engine is doing is not converted into useful thrust. There are a few ways to recover much of that tangential momentum and turn it into thrust. One of those ways is by using contra-rotating propellers, which are propellers mounted coaxially and spinning in opposite directions. By doing that, the rear propeller not only creates thrust, but also untwists or deswirls the airflow from the front propeller. The rear propeller therefore removes much of the angular momentum, leaving mostly axial momentum, and more of the engine's work is converted into useful thrust. While it's possible to convert virtually all angular momentum into axial momentum, that is not always achieved in practice. Still, contra-rotating prop studies and experiments have shown efficiency gains of around 6% and some even up to 20% over conventional propellers, which means more thrust produced for the same engine power. But if they are so great, why don't all propeller aircraft use them? Firstly, they can be mechanically quite complex, with additional gearing needed to reverse the spin direction of the rear propeller. This drives up design, manufacturing, and maintenance cost considerably. So, if they are used on turboprop airliners, much of the fuel-saving benefit can be offset by the higher cost and complexity of the engine. Secondly, contra-rotating props can also be very noisy, which leaves little room for them in civil aviation, especially these days. The Tu-95 is known for its extreme noise, even in cruise, but I'm not going to go into the more dramatic stories here. The reason for the noise is that the rear propeller blades cut through the wake of the front propeller, which contains a lot of vortices and pressure variation. That creates more complex interaction tones than with a conventional propeller. But besides the efficiency gain, the Tu-95 was never going to use anything other than contra-rotating props. And here's why. The Tu-95MS uses 4 Kuznets of NK12 turboprops, each delivering 15,000 shaft horsepower. To turn all that power into thrust efficiently, it needs a lot of propeller blade area. The obvious answer is to slow the propeller RPM down and make the blades as long as possible. But that runs into a practical limit very quickly because the propellers still need enough ground clearance. So the blades can only be so long. Another option is to add more blades, but in the 1950s, with the metallurgical limits of the time and no aviation composite blades to speak of, that pushed hub design into very complicated territory. An 8-blade propeller with a pitch-changing mechanism on every blade was simply not a practical solution for the era. Today, of course, it is possible, and we'll look at a relevant example later in the video. Using 4 blades per propeller with 2 contra-rotating propellers per engine not only made it possible to absorb the 15,000 shaft horsepower from each engine, but also brought those efficiency gains with it. But there are more factors that allowed the Tu-95 to reach those speeds. Looking at the Tu-95 from above or below, it's clear the wings have a lot of sweep, something not common on propeller aircraft. One major reason for that sweep is to reduce drag at high subsonic speeds. I've already touched on the compressibility effects when propeller blades approach around Mach 0.8, which create a lot of drag. The same basic problem applies to wings. By sweeping the wing, in this case by 35 degrees, the onset of shock formation is delayed. So it happens at a higher Mach number than it would with a straight wing. This comes down to the angle at which the air meets the wing's leading edge. With an unswept wing, the full free stream flow is normal to the leading edge. With sweep, only part of that flow is normal to the leading edge, so the wing effectively sees a lower Mach number in that direction. If the free stream is Mach 0.7, a swept wing doesn't see the full Mach 0.7 normal to the leading edge. Instead, the normal component is lower, and that makes compressibility effects less severe. The higher the sweep angle, the lower the normal Mach component becomes. As a result, at very high airspeeds, the wing has less drag than a straight wing would. But it isn't only about the drag from the free stream air the wing is moving through. Even at cruise speed, the propeller slipstream flowing over parts of the wing is even faster. If that local slipstream gets into the transonic range, shock formation can increase drag over those sections of the wing. Wing sweep helps reduce the component of that slipstream normal to the leading edge, which keeps it further away from the transonic region and lowers drag. Some historical write-ups and videos also note that the wing sweep helped move the wing spar forward to clear the bomb bay. I'm not saying that's wrong, I'm saying that whatever other design benefits it may have had, a swept wing also reduces drag at high airspeed. I've covered why blade tips going supersonic or even reaching high transonic speeds is costly for efficiency. And if it can be avoided, it should. But what if it can't? The Tu-95 has very long propeller blades, needed to absorb all that power and turn it into thrust. But as mentioned, the longer the blades, the higher the tip speed and the closer it gets to the compressibility problems associated with approaching the speed of sound. But even when propeller tips reach the speed of sound, the propeller doesn't stop working, it still produces thrust. And if you have the engine power, in this case 15,000 shaft horsepower per engine, you can accept a loss in efficiency in exchange for more thrust, even if that exchange is less than ideal. Lower efficiency will reduce endurance, and it will also reduce range if pushed far enough above the efficiency drop-off point. In the case of the Tu-95, the contra-rotating props, swept wing, and huge amount of power meant it can push the blade tips into the supersonic regime when the speed is needed, at the cost of some efficiency. And when more endurance is required, it can simply fly a little slower. And that is what the Tu-95 does most of the time. The maximum speed of the Tu-95 differs between variants. The Tu-95MS, one of the fastest variants, can reach 575 miles per hour or 925 kilometers per hour. That can be higher than Mach 0.85, depending on altitude because the speed of sound changes with temperature. And people often use that as a stick to beat anyone who says that the limit of propeller efficiency is about Mach 0.6. I get plenty of those comments every time I discuss propeller efficiency limits. But just because that's the efficiency limit doesn't mean it's the absolute limit. It can be exceeded and has been exceeded. That said, pushing any aircraft to its maximum speed comes at a cost. Engine wear increases, the airframe is under more stress, the propellers are under more stress, and the whole operation becomes less efficient and noisier. For that reason and others, the Tu-95 is not routinely operated at maximum speed. So yes, the Tu-95MS can reach 575 miles per hour. But that's its maximum speed, not the speed it normally flies at. What matters here is cruise speed, because that's how it's usually operated. Wikipedia cites its cruise speed as 440 miles per hour. I know how many of you feel about Wikipedia, but at least it cites a proper source, which does give this number. But I think one of the more credible information sources on the Tu-95 is Yefim Gordon's book, which gives the Tu-95M a cruise speed of between 447 and 466 miles per hour. This is close to that Mach 0.6 propeller efficiency drop-off point I've been mentioning pretty much forever. Quite interesting, isn't it? The propellers on the Kuznetsov NK12 are slowed down significantly with gearing to reduce blade tip speed, and they normally spin at 736 RPM. With propellers this large, 5.6 meters in diameter, the tips still travel at very high speed in flight, even at 736 RPM. We can confirm the tip Mach number with calculations showing the tip Mach number at 447 miles per hour, the low end of the M variant's typical cruise speed, and 575 miles per hour, the maximum speed of the MS variant. At 575 miles per hour, the blade tips are clearly supersonic, and at 447 miles per hour, parts of the suction side of the blade goes supersonic. To give an idea of how slow 736 RPM is, propellers on a light aircraft many people are familiar with, like the Cessna 172, turn at around 2,450 RPM in cruise. For more relevant comparisons, turboprop aircraft like the Beechcraft King Air 90 have propellers turning at around 1,900 RPM in cruise. The P3 Orion and C-130 Hercules turboprops have propellers spinning at about 1,000 RPM in cruise. Propeller RPM is thus a major factor in how fast an aircraft can fly. For fast aircraft, lower is usually better to avoid tip speed issues. We've also now established that the Tu-95 doesn't frequently fly at maximum speed. So when someone talks about the cruise speed of turboprop aircraft, pointing out that the Tu-95 flies at 575 miles per hour is misleading, because that's its maximum speed, not the speed it's actually flying all the time. With that fact established, how fast is the Tu-95 really when its cruise speed is compared to other fast modern turboprops? Enter the Airbus A400. Now before that, and assuming I've not angered too many of you, please consider supporting me on Patreon for some additional benefits. Links in the video description. The Airbus A400 is, in my opinion, the face of modern turboprop airplane technology. It was introduced in 2013, and in aviation terms, that is almost brand new. It is by no means comparable to the Tu-95, which is a strategic nuclear-capable bomber. The A400 is a military transport aircraft, and it is also about 60 years more modern, and it is fast, very fast. Yet, when people talk about fast turboprop aircraft, everyone mentions the Tu-95 and no one talks about the A400. The part that may blow your mind though is that the A400 is faster than the Tu-95 in operational use. The A400 can cruise at Mach 0.72 at 37,000 feet or 433 knots, which is 498 miles per hour or 802 kilometers per hour. Typical cruise speeds are between Mach 0.68 and 0.72. So 498 miles per hour is not its maximum speed, but its cruise speed, the speed it normally flies at. Operationally then, it can fly faster than the Tu-95. The Tu-95 flies at different speeds in different mission profiles, so I can't make a blanket statement that the A400 is always faster, but in many cases it is. And all that can be true without taking anything away from the Tu-95, which after all is a 1950s design, and an extremely impressive one at that. So how is the A400 so fast without such powerful engines, without contra-rotating propellers, and without extreme wing sweep? Isn't that what made the Tu-95 so fast? Well, let's not downplay it too much. The A400 is powered by 4 Europrop TP400 turboprops, each delivering 11,000 shaft horsepower. That is not quite the Tu-95's 15,000, but it's still nothing to sneeze at, especially since the A400 is lighter. To absorb 11,000 shaft horsepower, it uses 8-bladed composite propellers with a diameter of 5.3 meters. Modern engineering now allows what could not be reliably done in the 1950s. 8 blades on a single hub, without needing the complex gearing of contra-rotating props to absorb the engine power. The blades also have a moderate amount of sweep. The idea is the same as with swept wings. Sweep lowers the Mach number component normal to the leading edge, delaying shock formation and helping the propeller remain effective at higher speeds. The propellers on the Turboprop TP400 engine spin at around 730 rpm in normal cruise, slower than the Tu-95's, which is a big hint about the A400's high cruise speed. Doing the math shows how close the blade tips get to the supersonic regime. They are very close to Mach 1.0, but that is not taking blade sweep into account. The A400's propeller tips are swept back by about 55 degrees, so the normal Mach number is much lower than the absolute tip speed suggests. In other words, even if the tip is moving very close to Mach 1.0, the blade section only sees about Mach 0.57 normal to the leading edge. Blade sweep is therefore a key factor in the cruise speeds the A400 can achieve. The A400 wings do have a moderate amount of leading edge sweep, about 15 degrees, to support those high cruise speeds. It doesn't need more than that for the speed it cruises at. And modern technology allows the A400 to achieve those speeds without contra-rotating propellers. But there is another factor that plays a role in the A400's high cruise speed. Most turboprop aircraft have all 2 or 4 engines spinning in the same direction. The C-130, C-160 and P-3 Orion as military examples, and the Dash 8 and ATR-72 as civilian examples. The A400 doesn't only have counter-rotating propellers, but goes one step further with what Airbus calls DBE, or down between the engines. Yeah, I had to double check that one. What this means is that instead of both propellers on each wing spinning the same way, the A400's propellers on each wing spin in opposite directions, with the tips moving inward and downward toward each other. That helps create more symmetric flow over the wing. The way the two slipstreams interact is beneficial, as is the way the slipstream interacts with the wing, especially at low speed. The DBE counter-rotating arrangement also reduces yaw following a failure on one of the outer engines. This allowed the vertical fin to be made 17% smaller, which reduces structural weight and drag, contributing to the aircraft's overall efficiency and speed. There are even more benefits to DBE as well as other factors that contribute to the A400's high cruise speed, which I will not cover in this video. If that is of interest, let me know in the comments and I'll put it on the long list of planned videos. I hope this was informative. Remember to check out the Patreon links below. Thank you so much for watching this long, and I'll see you in the next one.